A very good morning to my supervisor, Professor Janminian, and also greetings to Dr. Bawadi from Malaysia. And so for today, I'll be presenting my SIP presentation with the title of Preparation and Characterization of Water-Induced Shape Memory Polymer based on polyvinyl alcohol, PVA, and also MMT, which is monomalonite. So without further ado, I will proceed with the outline of this presentation. So this is the outline of the presentation. So first of all, I will be introducing about this university, which is CGU, and I'll proceed to the lab, research project, which is my SIP, problem statement, aim and objectives, raw materials needed for the experiments, preparation of the membranes, example of the membranes characterizations, resource and discussion. And for resource and discussion, we have done a few characterizations, which is FTIR, XRD, TGA, DSC, DMA, tensile, and physical parameters such as thickness, swelling ratio, and polymer gel content. And last but not least, our main characterization, which is water-induced shape memory effect, and we will analyze by using recovery ratio. And the last part of this presentation, I will be explaining about the conclusion, recommendations, future works, and our upcoming conference. Okay. So first is the introduction of CGU. So basically, CGU is 10 years older compared to UTP, where it is established on April 1987, and it is located at Taiwan City, Taiwan. So basically, Taiwan City is almost 10 to 15 minutes to Taipei, and this university is also founded by Mr. Yun Ching Wang, which is the founder of Formosa Plastic Group. And basically, the initial aim of this CGU, of this university, is basically to train more medical practitioners due to severe shortage of medical doctors in Taiwan. So basically, CGU is almost the same like UTP, where CGU is collaborating with Formosa Plastic Group and UTP is collaborating with PETRONAS. So basically, for this university, we have three main colleges, which is medicine, engineering, and management. Alright, so introduction to lab. So for my SIP and SIP, I've done my research in laboratory of polymers for biomaterials and membrane technology. And for this laboratory, we have few research interests. So basically, we have three. So they are the synthesis or modification of polymers for biomaterials, preparation of polymerase scaffold for tissue engineering, and last but not least, the synthesis or modification of polymer for gas separation. So basically, in this department, chemical and materials engineering department, we have so many facilities to be used for research, and I don't think I can list down all of the facilities here. So I've listed down the main facilities that frequently used by researchers. So the first one is TGA, FTIR, DSC, UV, and also DMA, and many more such as SRD, FESM, and etc. So introduction to project. So for this project, so in recent years, many industries and academia, which is university, have put a lot of effort and very active in discovering new materials such as polymers, and because they want to diversify, they want to vary the applications in many fields. So basically, on top of all the polymers, we have one unique polymers, which is shape memory polymers, which exhibit one outstanding and excellent properties, which is shape memory effect, as we can see here. Because shape memory effect is very, very useful to be used for biomedical applications. And when we talk about shape memory effect, SME, what is SME? So basically, SME is when the shape memory polymers have the ability to memorize and return to its original shape, which is its permanent shape when it is manufactured, and it deformed to after it deformed to temporary shape. That means it returned from temporary to original shape. So this is the representation of SME, shape memory effect. So when we create the nanocomposite membrane, the initial shape of the nanocomposite membrane is straight like this, and this is the permanent shape, and or you can say as original shape. And after we deform into temporary shape, basically we can deform into spiral shape or twisting shape or anything. unless because we want to change the shape from its original shape, and we apply to investigate the shape mirroring effect. We apply some external stimulus such as water and many more. I will explain about this later. And after we apply external stimulus, it will go back to its permanent shape, which is the straight shape where it's originally manufactured. Alright, so basically SME. When I mentioned just now the external stimulus, what is the external stimulus? So this is the list. Basically we can categorize, we can divide the shape mirroring effect into many external stimuli. So basically the main stimulus is water induced, where the shape mirroring effect will respond when we contact the materials to water. This one is thermal, which is heat, magnetic or electric field. Light we can divide it into two, which is NIR and UV, which is UV is ultraviolet and NIR is near infrared light. And pH, where we change the pH of the solutions, and chemical, where we contact with another chemicals to exhibit the shape mirroring effect. So basically, what is the example? So basically, from after extensive number of studies and also learn about this SME. So from previous works, so the first one is the examples of water induced, the second one is thermal induced, and the third one is light induced. So basically the first one, water induced, after we have bent the membrane into torpedo shape and we immerse in water, then after some time it will become a straight shape again, which is its original shape. Same goes to the thermal. After we put some heat, it will exhibit the SME. And light, which is in this case is NIR, which is near infrared light. Alright, so for this research, for this project, what is the problem statement? So there are many successful researchers which include PVA, which is polyvinyl alcohol, as its base component, as its main polymer, and reinforced with other materials as the fillers. And we can observe that the PVA with other materials demonstrate the shape mirroring behavior. But however, not all material can exhibit this unique property, which is shape mirroring behavior. So basically, what we need to do before we conduct the research, we need to do a lot of extensive number of research study based on journal papers or articles that have been published, and because we want to investigate the possibility of SME when PVA is reinforced with MMT as the fillers, and we want to modify by cross-linking by using glutaldehyde and borax. And also from the references, from the journal papers, we will be able to get the conditions for characterizations. And what is the characterizations is that is suitable to be used to identify the shape mirroring polymers behavior. So basically, from the characterization, we'll be able to observe the improvement of these modifications. Alright, so what is the aim of this research? So basically, we want to develop the nanocomposite mirror by using PVA as the polymer, as the main component, and MMP as the fillers, and we want to modify by using glutaldehyde and also borax as the cross linkers. And the objective of this research is to improve the characteristic and properties of PVA through cross-linking and reinforcement and with MMP. So obviously we want to improve the characteristic from its pure PVA, and the main objective is to demonstrate the shape mirroring behavior of PVA MMP nanocomposite membrane, which might be beneficial, might be potential to be applied in biomedical applications. So experimental procedure. So this is the overview of the experimental procedure, where PVA polymer will act with MMT fillers, and we will get PVA MMT nanocomposite membrane. And from this membrane, we will add cross-linkers, and we will form cross-link PVA MMT nanocomposite membrane, which is our main polymer. Alright, so what is the materials what is the raw materials needed for this experiment? So the methods for the experiment that we have used, that we have selected, is solution custom method, because solution custom method is very economics, cost effective, and very easy to be conducted and easy to use. So basically the materials needed only 5, which is PVA, MMP K30 monomerylonite, deionized water, glutaraldehyde solution, and borax, which the scientific name is sodium tetraborate decahydrate. So basically all the chemicals are purchased in sigma aldrich, and we have used all the chemical as recipe and without any further purification. Alright, so for PVA MMP nanocomposite membrane, so this is the experimental procedure. So we want to make PVA solution 5%, and MMP will vary we will change the concentration, which is 0.5, 1.5%. So basically the first step is we weight the PVA powder and we dissolve in distilled water under continuous stirring for 1 hour at 98 degrees Celsius. And MMP also we dissolve in separate beaker, and we dissolve in distilled water and also stir for 1 hour at room temperature. And after we dissolve the PVA powder for 1 hour, we cool down for 30 minutes, and the MMP solution, after we stir for 1 hour also, we solidify it for 30 minutes also. After we solidify it, we add the MMP solution into the PVA solution, and we stir for 3 hours at 98 degrees Celsius, and the resulting solution we will cast into plastic petri dish and dry for 16 hours at 45 degrees Celsius in a drying oven. So to make crosslink, so basically it's the same step as 1 until 4. So for crosslink, we will make the glutaraldehyde and borax solution first, and also there are different methods to mix the glutaraldehyde and also borax. So for glutaraldehyde crosslink, the mixture will be stirred for 300 rpm for 30 minutes at 70 degrees Celsius. But for borax, only stirred for 200 for 3 minutes only at room temperature without any heat. So basically the resulting solution will be poured in plastic petri dish and also dried in a drying oven. So this is the schematic diagram of the experiment. So this is the method, which is solution casting method. So as you can see, this is we need to produce the PVA, we need to create PVA solutions and MMP solution, and we add. After that, we make borax solutions and we add with PVA MMP, and we cast. And this is the resulting membranes, non-composite membrane. So this is the example of our samples, which is this one is all membranes that are related to borax crosslink, PVA, MMP, non-composite membranes. So basically this is the list of samples that we have created. So basically there are 12. So PVA, PVAG, PVAP. So G indicates the glutaraldehyde crosslink and B indicates the borax crosslink. Same goes to this one. M is MMP, and 0.5 is 0.5% when we change the weight loadings, the concentration of MMP. And the concentration of PVA and crosslinkers, which is borax and glutaraldehyde, are the same, which is 5%. Alright, so this is the example of samples. So the first one is PVA MMP 0.5 with borax 1.0 and 1.5%. So we can see the concentration of MMP change the color of the membrane. So we can clearly see that the membrane's color depending on the weight loading of MMT. Alright, so for characterizations, the next part is characterization, because characterization is very important to know the properties of the nanocomposite membrane. So for characterization, we have done quite a number of characterizations. So the first one is FTIR, XRD, TGA, DSC, DMA, tensile, physical parameters, which is thickness, soil ratio, and polymer gel content. And last but not least, our main objective, our main aim is water-induced shape memory effect. So this is a picture of me preparing samples for SRD. Alright, so for results and discussion. Alright, so for the first one, FTIR. So the instrument we have used is Horiba FT730, and the mode is transmittance. This is the condition, transmittance mode, with number range 4000 per centimeter and to 400 per centimeter. Resolution 4 per centimeter, and number of scan is 16 scans. So this is FTIR. Alright, from the results, basically we can observe that the broad peak here, all this broad peak indicates the stretching variation of OH group in PVA. So basically this is pure PVA, this is all glutathione crosslink, and this one is Forex Crossing. So basically compared to PVA, the OH peak shifting to a lower wave number after the addition of MMT and crosslinking, where it can be suggested that there is hydrogen body interaction between PVA polymetrics and also MMT and crosslinking. And basically, as the weight loading of MMT increase, the intensity decrease. The intensity and also the wave number decrease. So decrease simultaneously. So basically, the intensity and the shifting of the OH peak of PVA is highly depending on the MMT and also the crosslinkers. Alright, so for SRD, this is the model that we have used, which is D2 Bruker. So the conditions are X-ray source, CUK alpha radiation, voltage equals to 10 kilovolt, current 30 milliampere, and range of diffraction angle to theta is 5 to 60 degrees Celsius, and the scan rate is 0.04 per minute. So this is the schematic diagram of SRD. Alright, so for SRD analysis, as we can see, the crystallinity peak, this is the crystallinity peak of PVA. So basically, after we add MMT, the crystallinity of PVA decreases as the MMT loading increases. So basically, from this graph, we can observe that a few characteristic peak of MMT, which confirm that there is interaction between MMT and also PVA in the nanocomposite membrane. And overall, the peaks of MMT are enhanced after we put are enhanced, and crystallinity of the nanocomposite is increased after cross-linking. So compared to here, with the cross-linking, the peaks is a bit short, and after we cross-link, the peak is greater than non-cross-linking. So for TGA, this is the instrument that we have used, which is TGA Q500. So the condition weight of samples is 5 to 10 milligram on a platinum plate. Heating rate 10 degrees Celsius per minute from room temperature to 600 degrees Celsius, and the sample push flow is 16 millimeter per minute under nitrogen atmosphere. So this is the result that we have obtained. So basically, it can be noticed that all the samples demonstrated multiple degradation. So basically, major decrease in weight occur at 250 degrees Celsius here. Here is the major degradation, where we will know that all the samples started to decompose. And as we increase the loading of MMT, the thermal degradation of nanocomposite is also increased, which indicates that improvement of thermal stability due to the thermal resistance of MMT. And from this result, basically, Forex Crossing showed the highest improvement of thermal stability, because from here we can see that because borax, we can know that borax is an excellent material for flame retardant if we compare with glutathione and also non-cross-linking nanocomposites. Alright, for DSC, the instrument that we have used is TADSC Q20, and the weight of sample is 3 to 5 milligram in an aluminium pan, and the heating rate 10 degrees Celsius per minute, temperature 50 to 350 degrees Celsius, and the gas flow rate is 50 milliliter per minute. Alright, so for DSC, after we reinforce with MMT and also cross-linking, basically the PVA, the melting point of PVA is 2 to 7. After we reinforce with MMT only, it becomes slightly lower, which is 2 to 6, and it is majorly decreased after cross-linking, which is with glutaldehyde around the lowest is 217 and borax is 199. So basically, the addition of MMT does not significantly affect the melting temperature of PVA. Somehow, the cross-linkers, which is glutaldehyde and also borax, affect the melting point of the polymer matrix. So for DMA, so the model that we have used is TA-DMA-Q200 and the frequency is 1 Hz. The heating rate is 5 degrees Celsius per minute and the temperature is 10 degrees Celsius to 130 degrees Celsius. And there are fixed dimensions for DMA, which is 30mm length, 5mm width and 0.15 thickness of the membranes. So basically, this is the results of DMA. So basically, the storage modulus of the nanocomposite increases as we increase the loading of MMT from 0.5% to 1.5%. So this indicates that an improvement in mechanical stability and also increase in stiffness in the nanocomposite membrane. So basically, from here, it can be observed that the cross-linking with borax significantly increased the storage modulus, where we can see from without cross-linking, the highest is 1400, with glutaldehyde is 1800, and without with borax is almost 7000, which is borax is the highest affecting the storage modulus of the nanocomposite. So it can be concluded that MMT and cross-linkers improve the mechanical stability and also increase the stiffness of the nanocomposite compared to pure PVA. Alright, so this is the tensile strength test. The model that we have used is GoTech, and this is the condition. Crosshead speed 5mm per minute, load cell is 100 Newton, gauge length is 50mm, and the specimen dimension that we have fixed is 16mm, 5mm and 0.2, which is thickness, width and also the length of the membranes. So this is the results, and as we can observe that the mechanical behavior is highly influenced by the loading of MMT. So as you can see here, with this one is 0.5, this one is 1%, and this one is 1.5% of MMT. So the stress of the nanocomposite is increased as the weight loading of MMT increase, and the strain is decreased a little bit, but somehow it is still improved compared to pure PVA, because because it increased the forcing effect and also the interfacial addition between the PVA polymer matrix and also MMT. Somehow the addition of borax greatly enhanced the stress, as we can see here. The borax at 5.5. Somehow the strain is decreased quite a lot, but the stress is greater compared to non-cross-linking and also glutaldehyde. So for physical parameters, we have three, which is thickness, polymer gel content, and also swelling ratio. So for thickness, we use digital thickness gauge, and the number of repetition is 5 times for different orientation of the membranes. And for polymer gel content, this is the formula, which is M2 over M0 times 100%. For swelling ratio is M1 minus M0 over M0 times 100%, where M0 is the weight of samples before immersing in water, and M1 is after immersing for 3 days, and M2 is after immersing for 24 hours, which is 1 day. So this is the experiment that we have conducted for polymer gel content and also for swelling ratio measurements. Alright, so basically from this table, we can observe that all the crosslink with borax nanocomposite, which is PVA-B, PVA 0.5B, PVA 1.0B, PVA 1.5B, dissolve in water after some period of time, which indicates that it is very soluble in water, and it indicates that borax that is cross-linked with the nanocomposite form a non-covalent bond. So MMT and also glutaldehyde form a covalent bond with the nanocomposite membrane. So as we compare the swell ratio, the glutaldehyde nanocomposite the swell ratio is more compared to without cross-linking, and the polymer gel content decreased a little bit. Somehow glutaldehyde has increased the flexibility of the nanocomposites. So for water-induced shape memory effect, which is SME, so this is the recovery ratio calculation, the formula. So theta I minus theta F over theta I times 100%, which theta I is the initial angle of the deformation, and theta F is the change of angle after some period, some interval of time. So basically, this is the procedure to investigate the SME. So first of all, we need to cut all the sample to specific dimension, which is 40 mm length, 4 mm width, and 0.2 mm thickness. And all the samples were kept in oven for 10 minutes at 80 degrees Celsius. And the samples were converted into spiral shape. If you want to, you choose other shape also can, as long as it is different from its original shape. With the aid of external force, as we can see here, we use paper clip as its external edge for 10 minutes at room temperature. So the purpose of paper clips is to maintain the deformation of the temporary shape of the sample. And after deformation, we can observe, we can investigate the SME by immersing all the samples in the ionized water. So after interval, for every interval, we use the digital camera, to observe the whole process of SME, including images and also videos. So from here, this is basically all path memory exhibit shape memory effect. So after, even for PVA only without including MMT, we can observe that PVA 420 degrees Celsius, 420 seconds to deform to its to return to its original shape. But after crossing with glutaldehyde and borax, it decreased significantly compared to without any cross-linkers. And for MMT also, after we add MMT to PVA, also they decrease compared to pristine PVA itself. And when we add the cross-linker, which is glutaldehyde and also borax, it decreased more compared to PVA MMT nanocomposite without cross-linkers. So this is the demonstration video of SME that we have conducted previously. So this video is just a short video because I made it for time lapse. So you can observe and enjoy this video. So this is the membrane. After some time, it is returning to its permanent shape, which is its original shape after we immerse in the ionized water. Okay. So this for this SME, we use room temperature condition as one of the conditions to investigate the shape memory effect. So now, the SME that initially spiral, which is returned back to its original shape. So for recovery ratio, so basically this I take one sample to analyze the SME. So basically for recovery ratio, the figure here we choose PVA MMT 1.5% with glutaldehyde. Basically, the change of angle is with the respect of immersion time is uniform. As you can see, the graph is just increasing linearly. So, and the non-composite membrane recovered to its original shape rapidly with only 155 seconds, and the recovery ratio is almost 100%, which is we can consider as very good as a shape memory polymer. So basically, the conclusions of this presentation is basically from all the results that we have obtained, that we have conducted all the experiments and all the characterizations, it can be concluded that cross-linked PVA MMT membrane, where we cross-link with glutaldehyde and also borax, have improved many properties compared to pristine PVA. And for shape memory behavior, the same cross-linked PVA MMT nanocomposite show the fastest recovery compared to PVA MMT only and also pristine PVA. And therefore, it is proven that many excellent enhancements that have been exhibited by the nanocomposite membranes after the reinforcement with MMT with the combination with cross-linkers. So for recommendation, so I only had for my SIT and also my SIP, there are only 2 recommendations that I find suitable. So the first one is the students that will have the opportunity to pursue in research discipline or will be involving in research discipline should be guided by lecturers beforehand in the university before they enter the university that they will pursue the discipline. So basically, the lecturers should teach them about how to do studies in terms of online research study, experiments, and also paper writing. And next is basically further research involvement should be made because with other industries and also universities, where this will improve the experience of the students and also enable them to relate all the knowledge that they have learned and apply the knowledge into many fields of research. So this is the future works that will be conducted. So the first one is for our lab, we are planning to publish a few journal papers that are related to PVA MMT nanocomposite. And basically, the objectives of this paper is mostly in the direction of shape memory effect (SME) and its potential applications. And basically, not only that, we will do more characterizations to reveal more properties of the nanocomposite membrane, such as contact angle, field emission scanning, electron microscopy (FSEM), rheology, and also optical microscope analysis. And last but not least, a conference will be held in our university where I will be competing in the student poster competitions. So basically, my poster will be related to the research that I've conducted here. So this is the upcoming conference that I have mentioned previously. So the conference is the 90th Asian Bioceramics Symposium and 2019 on December 9 until 11th, which is next week. If in terms of UTP's calendar is week 15, and it will be conducted in Universiti, Taiwan. Okay, so this is the poster that I have created, and I will present this poster in the conference next week. And hopefully this poster and all the data will be able to convince all the judges in the conference. With this, I will end my presentation with thank you. So I'll proceed with Q&A sessions.
So, yes. Show me DMA result.
Yeah.
So after the cross-linking of borax, its storage modulus is high. So it means that its mechanical strength is high.
Yes.
So what about the glutaldehyde?
Somehow
Also a little bit high, right?
yes, a little bit high, which is without if only PVA, it only like around 700 the story modulus, 700 MPa, and when we reinforce with MMT only, it will increase until almost 1400. With cross-link with glutaldehyde, it increased more until 1800, but borax increased significantly, very significantly, to 7000 compared to glutaldehyde, and also without cross-link.
Then what your conclusion? So borax is good for self-memory polymer, or only PVA is good for self-memory?
So basically, for shape memory polymer, both glutaldehyde, borax, and without cross-linkers, all of them is suitable for shape mirroring effect.
Without cross-linker.
Without cross-linker also, it also exhibit the shape mirroring effect.
Show me a self-memory picture. Yes.
Yes. All the samples exhibit the shape mirroring effect. And even after, if PV only 420 seconds, even after without reinforcement with MMT, we just add cross-linker, which is glutaldehyde and also borax, it reduced significantly compared to pristine PVA.
Okay, then next.
Next.
Then next.
Next.
Then go to your introduction slide. Okay. So then go to your tensile.
Tensile. Okay.
Then next.
Next.
Where is the tabular data? Only figure, right?
Yes, only figure. I just put figures because the data is too much.
Okay. Finish.
Alright.
Then send to this your UTP professor.
Yes.
Okay. And wait for his comments.
Alright.
What the valuable comment.
Okay.
So finish.
Alright. Thank
Okay.
you. So that's all for my presentation. Thank you.